Okay. The agenda for today is we're going to talk a bit about distributed train step capture, and then some time on Animesh's recent post about Dynamo graph break performance, and then Mario Liscano is going to talk about NumPy PyTorch. Wanchao, why don't you kick off the discussion?
Yeah, so just want to discuss about Will's point about the deferred init. So recently, I'm also learning that Alban and Michaela, they're actually developing some of the similar deferred init function. Is that something that we should actually uh have a holistic story about, or we use fake tensor? Like basically I'm seeing that the solution from Mikaya and Alban is using sort of like a meta device, and I was hearing that Will was trying to use fake tensor. Like do you guys have like a um a feel which one is like something we want to go further, or yeah?
NYC, take it away.
Uh, I don't know. I can give some answer, and I'll just look at me badly if you want to take over. Uh, I think at a high level, a couple of things I would say. The things we are looking to with Michaela today is more around skipping initialization, how to load models, stuff like that. Especially about replaying the initialization, so the deferred part, we are not working on. I want to make that very clear. We are looking at all the other problems that are very related, that very often get confused all together in one bundle. The whole point here was to actually unbundle them and to actually work on the ones that are actually actionable today. So that is what we are working on with Michaela in the context of NN modules. We can in parallel continue to have discussion about how to do deferred initialization. That is related, but non-blocking and relatively independent. So that's on the NN module side. On the optimizer side, I think there is an extra level of complexity in the sense that while on module, we have pretty well separation between initialization, like creation, initialization, and then runtime. That separation is not clear on the optimizer side. And in particular, in the way optimizers are usually implemented, these things overlap completely. Like there is no point where you could say this is where one ends and the next one stops. They are interleaved quite a bit. And so I think that makes that problem that we already cannot answer on NN modules even more complex for optimizers. So that's my high level view.
Yeah, I just wanted to add that with optimizers, at least, we could target. I think, Will, on your PR, I was like, lots of people use these Apex views and they come up with their own like EMA optimizer or whatever optimizer they want. And we don't really, there's no way we don't, like the contract we have there is not super well defined. Like there's init and there's step, and that's kind of what people normally do, but we can't control what they add in there. So like it would be good to know exactly what optimizer, or like is this supposed to be a general thing? Like we want to support all optimizers, because if so, that would require a lot more thinking and strategizing and probably reordering how this gets done. But if you're like, oh, I just want this to work with this one optimizer I'm currently hacking on, this is just a POC, then maybe, yeah, feel free to land it. But like, I have a lot of concerns about how the init is getting done, and it sounds like there are multiple steps that are stepping on each other. And I agreed that clarifying the use case of having, the module part be separate is pretty crucial, because the optimizer instance needs the parameters, and if you don't have those, that's kind of hard to, it's kind of hard to, the API will look different depending on separate graph versus like graph all at once or a separate graph.
Okay, let me try to. I feel like there's 3 or 4 points in there I want to respond to. So one was about the types of optimizers. I think we need to start somewhere, and also for this compiler in particular, we may not ever really care about the fused optimizers because we can't take them apart, or maybe we can. I think I'm probably wrong there. Like we don't necessarily need to trace into their ops, but we could still change the arguments, like which parameters we're going to call them over. So we might still want to decompose them in that way. So we'll have to figure out what we can do for those optimizers. But I still think it's useful to start somewhere and make progress on this. So that brings me to the next point about whether we should land it sooner or later. And the hacky init, the current PR has a thing that just zeros all the states after they're fake and once they become allocated. And I had this idea that maybe I can just take that out, and for the current PR, I can make it so that after you compile and run distcompiler, the model is real because it came real in the beginning, but the optimizer stays fake, and then the user is responsible for actually initializing the optimizer. That might be an okay starting point, just to punt this off to the user for now, and then the final, like the fix will happen in the third PR where we do deal with deferred init. And then in deferred init, we actually have to capture the init in a way that instead of the user needing to know it's Atom and call a certain thing on Atom, the initialization would have been traced and we'll just get replayed. Does that seem plausible?
Maybe. Okay. Well, two thoughts. One of them is I am slightly like, I agree it's good to start somewhere, but I would caution against thinking that, oh, if we get it working for Atom or if we get it working for any optimizer, it should just generalize. Like, I don't see that happening very easily given the current approach. And I do need to do more thinking. The second point is I do need to do more thinking about how the real and fake interaction and whether the user needs to supply anything or if we could get around that. And so that's, I guess for that point, it's like, maybe I should go and talk to you more offline about what the real plan is going forward. Like, if you need to land something right now just to like get somewhere or see what the problems really are, go for it. But I do feel like there is a lot of, like, there are so many obstacles that are going to happen when you try to generalize past this one thing.
Yeah, sure.
Yeah, I mean, definitely agree with Jen on that one. For your second point on can we just land that? My usual way of thinking about this is like, if you are within your prototype, I think it's you can just make the decision on whether to land it or not. I think the question opens up as soon as you start touching other components that you need to add extra logic in there, and that make thinking about these other components independently or your prototype harder. And I think one way to go about this very often is just what is the generic API or what is the generic thing you need from these components that you could add there that is not specific to your prototype that will allow you to do what you need in your prototype. That can be an avenue to unblock these kind of PRs. To say, within the Atom, I need that thing, or like within Dynamo, I need a callback that generally makes sense beyond your prototype. Maybe that will be an easier way forward.
Okay, I don't think I made any changes to the optimizers at all. So that part of the optimizer side of things should just be landable by that definition. But I'm still going to consider the thing I proposed a minute ago.
Yeah, and I would definitely agree with Jane that the only real contract we can guarantee you for optimizers is there's an init function with we have no idea what the signature is, and there's a step method, and we have no idea what the signature is. And that's if you want to go full generality crazy, that's the only thing we can guarantee you on our end. And so most likely you won't be able to do much with that. So we need to define, how much constraint you will want on your end, because, we cannot go and say, well, we will support everything at some point. I think we need to be clear that it's not going to happen. And we need to define the constraints so that we can actually verify it.
So the only thing I wanted to change earlier was like right now the init group function on the optimizer does take a bunch of arguments that are optimizer specific. So I can't really call it from a generic place because I don't know what the arguments should be. But I'm curious why we can't have an argumentless init that's just like optimizer.init. And then inside the optimizer class, it's responsible for feeding the right parameters from the optimizer into the init group.
So I think answer is the same for optimizer and similar for random modules is we don't control these. That's it. You know, we defined what these APIs were 5 years ago, and you know we don't control how NVIDIA implements their optimizers. And you know, for AMP, they added new arguments to the step function that they pass in for the fuse optimizers to do crazy stuff. We have no control over that, so we can't even guarantee you that the step function will take no argument or well-behaved argument because they actually changed that in practice in their optimizers. And so things like saying, oh, we need to add constraints to have an init function, you know, we could do that for the ones we have in-house if that helps as like an internal refactoring, but it's not a guarantee we'll have, right? If you say I want to support all optimizers, the guarantee is there is a step function and there's an init function, and that's where it stops. And for the next couple of years, we won't be able to give you more constraints, right? If we want to embark on a journey of every optimizer now needs an init function, we can, but then it's a multi-year journey we're going into.
I'd also like to
I think
add
that's
that.
fine.
Okay, these are the things that I think would be really good for me. Like, I think when you're like, here's my PR, what are your thoughts? That's like a little hard to parse out. But if you're like, these are the things I'm assuming about optimizers that if it were true, it'd be awesome. I can be like reasonable, not reasonable, or like we could work towards any of those things. And having that list of constraints, like what Alden was saying, would be good for discussion between us.
Yeah, I mean, I'm kind of a pass-through here because ultimately these constraints will be constraints to users. Like basically Discompiler will only work with a few optimizers or more optimizers. It's not whether train step compiler works with them. It's whether the end product works with them. So it's really a question for Discompiler. Like, are you okay with the fact that you can only support a few optimizers and maybe over time we can support more? And I don't see any choice. It's kind of just the reality.
Yeah, and I think that definitely agree. You most likely do want more constraints. Like the full unconstrained way is just too unconstrained for this compiler in the end. But you know, if we know exactly what are our constraints, we can actually test for them, or you know, have some guarantees that we will keep respecting them.
For that, wouldn't adding the argumentless init be a great way? Because then the contract could literally be, if the optimizer adds this support, then it works with this compiler, and if it doesn't, we get an error message saying like this optimizer needs to be updated, something like that.
Maybe, yeah, but we did, you know, like adding constraints to optimizer is not something we would do lightly. So if we have such a specification and we're saying, you know, for this compiler we need this thing and we have good reasons to do so, then yeah, why not? But you know, AMP is trying to put constraints on optimizers. You're trying to put constraints. Many people are trying to push constraints in here. So, you know, we definitely don't want to put ourselves in a deadlock where, you know, so we definitely want to be careful about that. So maybe that's the right constraint to put in, but we would need to discuss it for sure. And have good reasons. Yeah.
Ed?
I have a naive question, which is, so if I understand correctly, eager mode, DDP, and FSDP work with like whatever optimizers you want. Is that true?
Not really.
Not really.
Yeah,
So what is the constraint that eager DDP or FSDP has on eager?
I think most of the case it won't crash, but it does not guarantee to give you the correct or on-par result as local training. For example, if you are using a fused lamp optimizer where it needs to compute the norm for per parameter and maybe per layer, But in FSDP, if we're not using original, sorry, that part I don't know. But in FSDP, since we are flattening parameters, and then every local rank is only keeping a shard of the flatted flop parameter, so you're actually computing the norm on a different set of values. So it won't crash, but it won't give you the same results. So that's like some of the subtle details.
Okay, so let me suppose that when I say I want to FSDP a model with one of these, you said lamb optimizer, what I actually mean is I want to do FSDP with a modified version of the optimizer that only works on the local ranks data. In that universe, does everything work?
I assume yes, as long as the optimizer only consumes parameter and the gradients, and it fully contains its own like internal state, it should work with CDP and FSDP.
And I would say all of this is a very fine dance, by the way. The exact laziness of the optimizer versus whenever you wrap into your FSDP versus whenever we initialize things makes it so that it mostly works. Like in this case, for example, FSDP wrapping will shard, and because the lazy initialization of the optimizer happens after the first forward pass, any initialization, any initial sharding happening in there will automatically be taken into account by the optimizer. So a lot of these things are very much interconnected. Yeah.
But I guess the point that I wanted to make was that basically there is some set of constraints that FSDP and DDP impose today, and under those constraints, people have been allowed to do whatever they want. So I feel like there should be a way to also get it to work in the compiled setting without having to add more constraints. This is not a plan, but this is just an intuition, which is that if you can do it in eager, then you can do it in compile, because compile is giving you strictly more rope than eager was.
So I think that, I guess Shen can respond to this more, but there's two flavors of compile, right? We could probably build compiled FSDP and compiled DDP without any more constraints. But I don't think we need full train step capture for compiled FSDP or compiled DDP. The train step capture plays into additional optimizations that the disk compiler wants to do that are beyond what's possible with eager. And that's what you need to justify these constraints. So I think that's the discussion, is are these extra optimizations, cross-iter optimization, worth it or not worth it? Because they need the extra constraints.
And just for the sake of knowledge sharing, I don't know, Shen, Wenchao, do you want to just tell us about some of these optimizations?
Sure, I can maybe share my screen. Give me 1 second. Can you see the slide?
Yes.
Cool. So these are some of the optimizations that we want to do with full train step capture. The first row, let's assume that's just the vanilla DDP where we already have fused already used. And this is assuming we have a Rexis model, where in the beginning we have some model for the sparse part, and then we have forward backward compute and already used for the dense part, and then we have optimizer. So the first thing we can do is what Will mentioned before. We can split, say, a fused atom into 2 parts by splitting the parameters, and then place some part of our optimizers to overlap with the later part of our reduce and auto in the backward pass. And then additional things we can do is we can analyze the dependencies for the sparse part, basically having a graph having a layered graph where there's only dependencies between layers and all auto within the same layer, there's no dependencies. So we can fuse every auto within the same layer into one like grouped collective. And another thing we can do is that in this case, the first auto actually does not depend on any subsequent computation. So we basically can launch the first auto for the next iteration earlier. So in the fourth row, the red auto is actually for the next iteration. That can be overlapped with some of the forward and backward computation. And additional things we can do is that there are still bubbles in the beginning and at the end. We can postpone some of the like optimizer step and some of the reduce in the previous iteration to the current iteration. So you can assume that the purple optimizer and reduce are actually from the previous iteration. So these are the like typical optimizations that we can do if we have a full train step graph.
Okay, so I just want to say something that's wrong, but hopefully it'll spur discussion. So the wrong statement I'm going to make is this can be done by data dependency analysis. You don't need to have any extra structure from the optimizer. Tell me why I'm wrong.
By data dependency, you mean eager or?
No, what I mean is I don't need to know anything about the optimizer. I just need to like I can trace out the optimizer. I'll get out a bunch of, takes in these inputs, it, writes into these outputs, and then, figure it out from there. I don't need any more structure from the optimizer.
If we can split the optimizer based on that data analysis, I think yes, but I don't have a full context on like how we're going to do that data analysis.
Okay, so that's a good point. So point one is that if my optimizer is this big fused thing, opaque, and it takes in all the parameters, then obviously I can't split it because I have no idea how to split it, right? So in fact, it sounds like you would much prefer to have a trace where the parameters haven't been fused because you want to, you want to make the fusion decision yourself. Is that right?
I think maybe we have worked on the optimizers with the for each version and the fused version. I think in both cases we can split. But if it's like per parameter version, I think it will make the algorithm a little bit more complicated, but it's also doable. So I kind of feel all the three cases we can do this splitting thing.
And the for all case you can split because you know that you know something about the for all operator that like you can chunk the input and then it'll still work.
Yeah, we can do the like arguments dependency analysis and see how to share that, and also how like which version of optimizer is used in the train step is not determined by us. It's basically user decision.
New York?
Yeah, I was gonna basically say yes, Shen, because the updates don't talk with each other, so it is fine, like with any of the implementations you were talking about, at least the ones we offer in core, to do that split, like bucketization that you want to do. So that sounds right to me. I think Alvin.
Yes, but it was more coming back to Ed's like why is this statement wrong? And when I look at these graphs, they very much remind me of a lot of the CUDA execution ones where we say, oh, this is what happens, how our CPU and CUDA align with each other, but the asynchronous execution or different streams allow us to do this kind of like compaction. And I'm curious, to what extent do you think in this world, a synchronous stream like execution model would allow you to get this kind of packing, assuming you can remove most of the synchronization points with the model?
Sorry, I didn't get the question. In the world of synchronous training, like to what extent I can capture the graph or move things around?
So like if we remove the distributed collectives from this graph, I could write a training loop that does no synchronization, including at the end of every iteration, so that I can make the optimizer overlap with the next iteration, just by design of like, GPU execution will be delayed. And so, when my CPU is executing the next iteration, my GPU is still running the optimizer from the previous iteration. I could imagine being very strict in my code to get this kind of behavior. And if the collectives are like in a similar streaming fashion of like they just asynchronously happening and synchronized with the GPU code, you could see that idea extend to these kind of things where we launch the next iteration all to all in a very synchronous way, and so it will happen where it will happen kind of deal, and our CPU is way ahead kind of scheduling all of that.
Alban, but I'm just saying that Ed is right, and all that's needed is tracing the operations and dependencies, and then just have a scheduler that could use different streams depending on what's ready to go.
Okay.
That was the question. So, do we agree that we don't need to impose any additional restrictions on optimizers? We just need to be able to trace through the optimizers, and then this compiler will be will have enough information to make optimum decisions.
I
No.
cannot make that claim on the current information.
Okay.
No. So like, there's one thing I will say first. There's two problems mixed together. Like, the only constraint we want to add is a way to capture the initialization of the optimizer, which is not at all relevant for optimizing it. Like, doing the split doesn't require us to add any new constraints to the optimizer. The only thing that matters is making sure we don't end up with the optimizer in it somehow captured into our graph trace.
Yeah. Basically, like if we cannot correctly trace optimizer at this point. This is the current system, because if we trace it, the first time we trace it, there will be all the torch zeros inside the graph, which is just insanely wrong because we don't want to run torch zeros again and again.
Sorry, I guess maybe I tried. So I remember when I was trying to trace the optimizers, the two main obstacles were basically that like one. It's basically what Wenchao said, which is like the state is implicitly materialized on the first time you call .step, which is very annoying from like a tracing perspective. And then the second factor is that there's no kind of equivalent of like a module.functional call with an optimizer, because like the requirements for tracing are basically you need to make all the values that you depend upon like inputs to your graph in some sense, right? And so with the modules, the way we do this is that we grab all the named parameters and then we grab the functional call. With optimizers, there's no like clear equivalent way of doing that. And so it was very annoying to actually do so. I'm not sure if things have changed, but basically there's like some hacky stuff that you kind of needed to do.
Don't all of our optimizers now have functional step that takes in all the parameters that it will depend upon? So
Yes.
Yeah, it has,
so I think we can solve that part, but the init part is just awkward. Like I don't think there's a very clear solution to the init part yet.
Wanchao.
Sorry, I just want to say, there's a functional call. Actually, we did this a while ago, but the lazy initialization is still built into the step itself. There's no way for us to preemptively do it. So that, like what Horace said is that we have hacky hacks. We have to warm up the optimizer once by calling the step once, and then trace the optimizer so that we can clearly get the states out of the leave the states to the functional call as an input argument. That's a issue that we're currently facing.
I wonder is a recompilation an option here? Basically recompile for the second iteration.
I mean, there are lots of things we can do. This venue isn't really the right spot to we could, but we probably need like 2 more hours to like grind through the rest of the details. I mean, yes, I think you guys have options. New York wanted to say something too.
No, I just wanted to say that we have 20 minutes left in the meeting.
Yeah, that's fine.
And I have more comments, but I can do that offline.
Yeah, we'll keep talking about this. All right, Mario. Sorry, Animesh, I'm gonna skip over you. Mario, you're here, right?
Yep.
All right, let's get going.
All right, let me just share the screen. Yeah, I just wanted to like walk over a little bit like with the work that we've been doing at Quantsite on the PyTorch numpy compatibility layer. And this is like I mean, you might have already seen it in the post I put up in Workspace, but it's just a reimplementation on NumPy using PyTorch. That's it. Like there's nothing more to it. And there's the RFC. I'm going to basically walk over it, basically discuss a little bit the decisions that we took, and then there's an open problem that we didn't want to, want to gather some feedback from you guys. And yeah, so that's sort of the plan. The summary of this is like we want to make Torch Dynamo understand NumPy calls. So in order to do that, we want to be able to translate NumPy calls, which are very, very similar to PyTorch calls into PyTorch calls, but like there's many, like very many details that are slightly different. Like for starters, like the default D type in NumPy is float 64, PyTorch float 32, and there's like quite a few other things that are happening behind the scenes, and like quite a few quirks that NumPy has. So that's on how to do this. Like we split in two parts. One is we'll implement NumPy using PyTorch, just an object which is just a wrapper around PyTorch tensor, and we'll dispatch all the calls into PyTorch calls, and then we'll have we'll implement, or actually someone from Meta implemented bindings for this NumPy ND-array like object in Torch Dynamo, and then whenever you are tracing through a function, the Torch Dynamo will wrap all the NumPy tensors into this object, and we'll turn them into Torch tensors. We'll trace through the whole function, and then we'll return NumPy. So it will preserve the semantics, but it will do like this wrapping and wrapping at the beginning and at the end. The whole idea, I mean, like, there's just a few examples and like a few of the quirks that, it's discussed, like we discussed here, a few of the quirks that NumPy has, like for example, the default D type in the whole NumPy is float 64. And then like, there's another thing that I'll touch on later, that there's this thing that reductions and things that return 0D arrays in PyTorch. In NumPy, they return these things called NumPy scalars. In this case, like you have here a NumPy.float64, which doubles as a D type and as a constructor for NumPy scalars. So, you know, there's like just a few different that we have to deal with here. But the idea is like, yeah, you transform each of these calls into the equivalent PyTorch call. Here you have some other example where you have like just some tensors, and you want to pass them to a NumPy call, to a NumPy function. If these tensors are on CPO, this already works because Anijan, you have a question?
Yeah, just a quick question on the random. Does NumPy random has same results as Torch random?
Yeah, that's a
Not
very
at
good
all.
question. Yeah, we discussed it down there, and the answer is no. And there's no way that we can actually do that. So the randomness will be different, and there's like the random number generator that PyTorch uses and the random number generator that NumPy uses, they're different. So there's nothing that we can do there really.
Yeah, so maybe we should have a flag, sort of like fallback random, just in case if people want the same accuracy as eager.
All right, we can discuss this a little bit later. Like, let's first go on to, you know, like what like how would this be used, and then like figure out with it. So yeah, this code like is just a function that uses NumPy. This code at the moment, and like if you feed it to Torch tensors, at the moment it just works if the tensors are on CPU, because we implement the Dunder array.
So numpy knows how to handle objects that implement under array, and like it basically casts, well, it doesn't cast, like it doesn't copy anything, just knows how to use the memory from PyTorch on CPU and like execute numpy functions. So this already works, but like it wouldn't work if you pass it like CUDA tensors. But the idea is that like, all right, now we want to trace through it. So this whole idea, this whole implementation would allow you to trace through this little program or through much larger programs, just like tagging them with compile, and like everything should work. That's sort of the idea. The main design decisions that we took can be summarized as like, we want to transform valid NumPy programs or like mixed PyTorch and NumPy programs into their PyTorch only equivalents. And by valid here, I mean like, you know, we will not care about like exceptions. And this is one of the things here, like exceptions may be different. We don't want to, you know, go down the rabbit hole of like throw in exactly the same exceptions as in NumPy, because we've seen in PrimTorch that is a massive pain, and it would take us loads of effort to just like throw in the same exceptions. And also something that follows from this first idea, that like transform valid programs, that we are actually implementing a superset of NumPy. So we do not necessarily want to just implement NumPy. Like we can implement something that is like more even than NumPy. So if NumPy almost always accepts these sort of objects as inputs, but not always, perhaps there's some functions that they haven't implemented it. Like we will implement it for them all, and like we can do that in a more generic way. Second idea is that the behavior of the layer should be as close as NumPy as possible. All right, fair enough. Third one, the layer follows the most recent NumPy release. The idea here is that NumPy has like loads of like behavior that's very much not recommended, and like loads of legacy behavior that it has accumulated throughout the years. And in particular, one thing that is like absolutely mental is this point in type promotions. Like type promotions on NumPy are data dependent. So if you add a number that's too large, like basically scalars are casted to the smallest type that can hold them. So, you know, like depending on whether you're adding 127 or 128, you will get a different D type. This is absolutely mental, and like NumPy maintainers know about this. And they're going to change this in NumPy 2.0, which is planned for the end of the year. And it will be replaced with a proposal which is called NEP50 that removes all this like very, very weird behavior. So we went on and we just implemented this NEP50. Like Ralph recommended that, you know, that's going to be the future. And like at the moment, like these things are more like quirks than, you know, something that we want to replicate. So, you know, like that's what this is one of the things that follows from the idea of like we want to be following eager rather than we want to be following like the lastest NumPy release, and in this case like even a release that's about to come, because that way like we don't need to implement all this very odd behavior. Another thing that we chose is that default details we wanted to leave. Well, from the second point, the behavior of the layer should be as close as that of NumPy as possible. Is that the default D types, we are going to leave those from NumPy. We are going to we are exposing a global flag that allows you to change the default D types of the whole system to flow 32 and so on. But by default, it's going to be just as NumPy. Like JAX went the other way, and they like historically they are sort of regretting it. Like it's along it's listed in the list of like sharp edges that JAX has, and so by default I think that things should work, and that's what we went for. And then if people think that, you know, they should change things, they should actively change them, like rather than like us choosing for them. Another thing that we changed is the NumPy scalars. NumPy scalars are by definition on CPU, so that wouldn't work with like we want to trace through things and like keep it potentially run things on CUDA, like just that wouldn't work. And like as we've seen, like NumPy scalars happen everywhere, like a return, like it's returned by np.sum. So, you're certainly going to encounter them. NumPy scalars have like a very weird behavior. I mean, not weird, but like they are basically like Python scalars, but with a fixed width. And they also decay into, as shown here, they decay into Python scalars in some cases. Now, these cases are a bit weird, and it's like just when they interact with other like Python objects. But in our cases, what we did is like all these operations following the PyTorch, like we deviate a little bit from the second point that we enumerate up there. And in this case, like we are not implementing NumPy scalars because like that wouldn't work with tracing and CUDA. Like that would be, you would end up having like graph breaks left, right, and center. We are just returning 0D array objects as we do in PyTorch. And what version we've already mentioned, randomness, we've already mentioned that randomness is just different. And accuracy, like the desiderata in accuracies would be that similar to torch compile, we will expect the decompositions that we are implementing to be as precise to those from NumPy compared to an FP64 baseline. So it's basically the same idea as in torch compile. Now I'll just touch very quickly on like the only thing that's a little bit, let's say, interesting in the whole implementation. As to like how we
Actually,
did
Mario, let's take a brief break. NYC.
Just wanted to come back on Animesh's comment on the randomness, bitwise equality of randomness. I think the accuracy point here definitely limits significantly the benefit of exact randomness. So I don't know, how much engineering we want to invest into getting the same randomness, given the accuracy guarantees that we provide.
I don't think that's what Animesh was asking for. I think Animesh was just saying, hey, there should be a way to easily just call into NumPy for random operations only, so you get the same random numbers. Like, we have this for Dynamo Inductor. Like, it's fine. It's not too hard to implement, and it's a good idea. Vaz?
Hey, yeah, this is super cool. Very naive question. Have you looked at this with dynamic shapes potentially? And do you expect any sort of interaction between this and dynamic shapes? Like, I don't know, what happens if I have an ND array with a bunch of Simmons in it? Is that like a unhealthy intersection, or will it just all kind of work?
I would expect this to just work because this is just an implementation of NumPy in pure PyTorch. Like, there's nothing funny going on here. So if you can trace through it, like, I wouldn't, it would work as much as it works for any other PyTorch program.
Well, if we graph break and go back to NumPy for like some weird FFT op that we don't support, and it had a cement in it, then something weird would happen, right? We probably want to at least catch that case. But I think otherwise what you said is
than when you hit a weird PyTorch op that we don't understand and we go back to error mode.
And there is no NumPy here. Well, we never fall back to NumPy. We fall back to our PyTorch-based implementation of the NumPy op. NumPy code never runs.
No, I mean, like if you have a code that uses like 4 NumPy ops and 3 of them we support via PyTorch, but one of them is totally weird, then we would graph break and fall back to it, right?
But yeah, like as Ed said, like it's literally the same in PyTorch, really. Like if you hit a very weird operation in PyTorch.
Yeah, I think that's fine too.
Yeah, I have a question on the plan on the NumPy torch interop. Will it be upstream to PyTorch?
Yeah, that's the idea. That was like later down the discussion. I don't know if you guys want to discuss it now.
Let's just hop there real quick, because I don't think this depends on the Torch NP presentation. Did you just want to talk about it real quick?
Do you want me to discuss the upstreaming?
Yeah, let's just talk about upstreaming real quick, and then we can come back here.
Oh yeah, so there's the RFC. Like I would expect, like if you guys have like questions and comments, like well, you have this all here, and all this implementation is just like pure Python and like just a very thin implementation. Like very simple implementation, like probably like, I don't know, no more than 4,000 lines. I don't think that should be particularly difficult to upstream. The only question that is left open, and that's at the very end, is whether this should be public or not. Should we just use this internally in Torch compile and make this just work, or should this be exposed under, say, torch.numpy similar to Jax? Here I enumerated like a few pros and cons, and I know that people have like different feelings about that, but yeah.
Any opinions from the room?
I guess I'll say my naive opinion, which is that like it does feel like, you know, doing like import torch.numpy as NP is limiting, right? Or like in the sense that, you know, like if you call into another file that is also importing like numpy directly, then like this kind of, you know, shim doesn't work. So you, at the very least, you need to make sure that you, or I guess part of this to me is kind of dependent on like who do you expect to be the main users here? Like, are there any like large NumPy code bases that we kind of expect people might just be able to get like out of the box acceleration with, or is this kind of meant to be more? I guess I'm curious. Like, what is like the scope of like applications?
Yeah. So for reference, like we designed this having in mind that this would be traced through. So the eager execution is not like the speed is not great and it's not optimized for that at the moment. So that's an issue with like exposing it. Like people, like you would be exposing like an API very similar to PyTorch, but that's way slower. So, you know, on the other hand, like people could potentially like just use it out of the box, like just replace their numpy as NP import with this, and like they could start like playing with it and then use torch compile later on. The users, we have not identified like a large code base to test this on. Like we have tested it on like small bits and pieces, because like mostly like all the like numpy based libraries, usually they also mix up like some Python and like some other things that we don't support. So it's been difficult to find like a pure NumPy large, well-maintained library.
Or but like even like when they have like manual Python, we should still be able to like compile the regions that are written in NumPy and then like, you know, fall back on the Python components, right?
Yeah, but at the moment, like that's true. But at the moment, we've just been working with this like assets. We were not using like Torch Dynamo. Like now that the bindings have been merged, like potentially we could like try it on those in the larger code bases and see what happens. But like, so for context, like we have tried this something similar, and like it's a different project, but like slightly similar. But like there's consensus in like scikit-learn and SciPy to use the array API to be able to execute their functions in PyTorch, and they've already been trying that, and they've tried that in a couple operations in scikit-learn, and they were getting like a 5-fold speed up on CPU and like a many-fold speed up when using CUDA versus CPU. So yeah, like potentially like this could be really useful even for like for pretty much any user that uses like all the PyData stack. Yeah. So and also like more generally, it's a good selling point of PyTorch. You know, like if you know these other things, all right, you can just use it. Right. You know, it's a good entry towards PyTorch.
No, I definitely think it's like super valuable and it's something like I kind of really wanted for some time, but I'm just kind of curious whether like that we can kind of, even people who have like no interest necessarily using PyTorch directly, whether there's kind of applicability or like, you know, they've been using NumPy for a long time and then they just have like a large NumPy mixed code base, whether we can kind of provide value there as well.
Yeah, I think so. Like I think so. Yeah. Like NumPy is not particularly like NumPy usually goes for like accuracy rather than speed, and like PyTorch usually does a much better job at vectorize and stuff even on CPU. So usually you get like a twofold, threefold speed up in many normal operations, and if you fuse them, like even more. So
To answer the original question, my feeling is that, well, there is going to be this torch.numpy array API no matter what you do, right? Because that's how you structure the code internally. So like, if someone wants to like peek under the covers and use that, like, we're not going to like block them from doing it. But I do think that in terms of public API, one of the reasons why we never did torch.numpy was because it's this huge new surface area and we need to maintain it. And oh no, it doesn't interoperate with NumPy. So like, I would be very comfortable with like only really advertising the Dynamo integration to start. And, I mean, if you want to like change your mind later, you always can, because you can always add another API. You can't take an API away in the future, though.
yeah, that's what I think as well. I think that a priori, like, it's better to be conservative, and then like we can change our minds.
Okay, Mario. You've got a minute. Oh well. Sorry, Horace.
But like, if we, so I mean, the way I'd imagine this, right, or like, like the way we do it is we basically just kind of integrate the code and basically automatically, essentially, like we are supporting it anyways, just only within Dynamo, right? So like we would still need to like have a lot of testing around, all the NumPy ops are translating into PyTorch and so on, and we would just like put this in Dynamo and basically. I mean, like, today we only capture torch operations Dynamo. Now we would also capture NumPy operations as torch operations.
That's right. But the point is that, like, if there are sharp edges on the torch.numpy API, which there will be, right? Because you can't just use NumPy operations on it. We don't have to feel obligated to fix them, right? It's like you get this technical mechanism with all the warts, and we're not trying to make the UX good. Like, we'll do whatever's easy and we won't do anything that's hard.
Okay, sure. Yeah, I do agree. Like, exposing it as like a completely separate API, is well, no, I kind of do feel like we should expose it as like a separate API. It feels kind of weird to me, because like for example, like you end up with like weird situations where like let's say you have like a NumPy function and you want to use it, to like you want to use the middle of the code and you want to propagate gradients through it. Like if you use it under the context of Dynamo, then this is like you can't, right? Like we can capture the whole thing with torch operations, and then you can propagate gradients back through it. But if you get rid of torch compile, then all of a sudden you can't propagate gradients.
But to be clear, Horace, this is scope creep, and it also assumes that the NumPy decompositions are differentiable, which Mario.
We try to make them differentiable.
You try to make them differentiable.
Like, yeah, just in case. Like we try to avoid grab breaks whenever possible. We try to make them differentiable whenever possible. But it's not tested. So yeah.
Yeah, I mean, I guess my feeling is like I have like a weak preference towards making them public, but perhaps with some pretty explicit, like like guaranteed, like you're not intended to like use this to, you're not intended to use this to like automatically, or like you're not intended to use this like, by itself just to replace NumPy.
Yeah, I'd say a non-goal would be to like have an existing NumPy code base work under PyTorch, right? You should use the Dynamo integration for that. I would also say a non-goal was to get good performance with it, or the best performance with it, right? And it would also be a non-goal that you would use this instead of the PyTorch API just because you prefer NumPy APIs over PyTorch APIs. These are all things that I would not say were intended use cases.
Or I think the third one seems, or like using it as a replacement.
It sounds very plausible, right? But I don't like, because if you're like, I prefer NumPy API over Torch API, then we have to have a big discussion about, but can we make this smoothly interoperate with Torch operations if you want to use them? Because like, if you're using it as an alternative to the PyTorch front end, then we've got to answer questions about what happens if I do a torch op on one of these torch ND array things. And
Wait, sorry, these are just sorry, perhaps I assume these are just PyTorch tensors. They're not like some
the
special.
inside is a PyTorch tensor, but
Oh, the
They're
outside is like this
wrapper.
ND array.
yeah, there's a wrapper around it.
I see. I think I missed that.
It's just a class with one dot tensor.
Oh, I see. Yeah, I agree. That definitely does make the question a bit harder.
And it's not unsolvable, but like, you know, it's way easier to just not worry about it.
Or like,
or sorry. And you can potentially like expose it as experimental. I think that like it would be good for people to be able to just like, you know, just import this other thing. Like you get if you get errors, the errors are like very simple to understand. Like, you know, you get a frame that's like 3-4 lines rather than like the whole torch compile that you are like, all right, is this torch compile? Is it my code or is it the, you know, like it would make much easier to adopt this and like to be tested by people. And we're going to have this tested. Like I don't really buy the point that Ed made before saying that yeah, like we don't really need, since we are not exposing this, we don't need to test. No, like we are, like if we are upstreaming this, like we'll need to maintain it. So yeah.
Or so actually, I realize this. Like, how is this meant to interop with torch operations today? Like, if you have like a torch tensor and then you add it to like an NP array under Dynamo, what happens?
So whatever. Yeah. So the idea is that whatever works on Eager should work on Dynamo.
But this won't work in Eager, right? Today.
It does, but because we define
CPU.
array function or something like that.
Yeah, then the array, yeah.
The PyTorch tensor gets coerced into a numpy ND array, and then you do the ND array operation.
It's literally what torch function was based off. You know, numpy had that worked so well that we copied it.
That's it.
All right, we're out of time, so there's going to be the FunkTorch hangout right after this. So you know, we can chat some more. Mario, do you want to pop in if you want? Actually, I think Elias wants to talk about something else in the FunkTorch slot. So, all right, but thanks everyone. Thanks, Mario, for presenting.